Again, in this video, we'll wrap up chapter 14, retirement planning. There's no mini exercise associated with this video, but it'll be helpful for purposes of completing the last assignment. And if you remember in our previous video, we left off with the basic retirement savings example, simple fact pattern, and we're going to approach this in Excel. So actually under in-class, other resources, I've uploaded a spreadsheet that we'll work off of. And in the first tab, we've got the same information a place to put in the information about the problem that we need, right? So we've got 400,000 saved for retirement, living for 20 years, need $50,000 a year, right? Is this going to work? What return would the client need? So we'll be finding the discount rate, right? Solving for an interest rate that can make these retirement cash flow needs funded by this $400,000 nest egg. So let's put in the relevant parts of the problem. 20 years, got an annual problem here. We're going to withdraw $50,000 a year, so I'll put this in as a positive number. That's the payment. And then the amount we have saved at the time we retire is 400,000. I'll put that in as a negative number. It should be the opposite sign of the withdrawals. You could switch the signs as long as you are consistent throughout the problem. I like to think of it as, okay, how much money do I put into the retirement savings, right? Or do I start with? That's a negative number. And then the withdrawals are cash inflows that I consume goods and services with. I put those as positive numbers. You can figure out what works best for you. If you've got questions about it, just let me know. Okay, so here's the relevant information in the problem, right? We need to make this $400,000 last for 20 years, withdrawing $50,000 a year. Right? We'll end up with nothing at the end in the assumption of this problem. And so to figure this out, right, with just an annuity of retirement withdrawals, we use the rate function to solve for the discount rate. What return do we have to earn to make this $400,000 last 20 years and fund $50,000 withdrawals per year? So the first argument, 20 years we save for. Annual withdrawals are $50,000. We start with $400,000, negative $400,000 is present value. And that's all I'll put in. What comes out is 11%. If I remove the number formatting, Control-Shift tilde, we need to earn about 10.93% to make this $400,000 last 20 years. Okay, seems a bit optimistic in retirement, but illustrative of the facts of the problem. I've also got like a vertical cash flow timeline here that I'll illustrate the problem the same way. And if we start with, I'll express things in thousands here. Start with 400,000 in year 0, and then years 1 through 20. Enter the number 50. Control Enter will fill this down. Right, we make withdrawals of $50,000 per year. What discount rate gives these 20 annual withdrawals a present value that adds up to exactly $400,000? The IRR function is set up to tell us that nicely. We should get the same result if we use the IRR function, the internal rate of return of this cash flow stream. Comes out to be 11% again. And then if we remove the formatting, it's the same result. So let's look at a couple other examples just to provide some context. On tab 2, sheet 2, we've got a 10-year horizon and then just some simple forecast retirement expenses just for illustrative purposes, right? So housing seems to be fixed, $1,000 a month. And then here's some other expenses, who knows what they entail. And then the total expenses is just the sum of these two. So a slightly different question. In order to fund these retirement cash flow needs, how much do we have to have saved, right? And the answer is, well, it's the sum of the present values of these cash flows. We've got a discount rate, 5%. That's conservative, right? A low discount rate, a low interest rate on retirement savings is more conservative. And to find the present value of all these cash flows, right? This is not an annuity, so we can't use the just PMT function. But we can find the present value of these using the NPV function, right? How much do we have to have saved? Right, the answer to this question, well, we could use the NPV function, equals NPV. Discount rate is 5%. That's the first argument. The second argument is all the future cash flows, right? Starting with year one. So this problem is set up to use the NPV function nicely. And so if we find the net present value of this cash flow stream, given the discount rate, we would need to have about $178,000 saved to fund all these future withdrawals. So that's another approach to retirement planning. If we know how much, well, if we have a forecast of the cash flow needs, right, and an assumed discount rate, we can figure out how much will I have to have saved. And then finally, on this last tab, similar to the first example, but a little bit more complicated in terms of, okay, it looks like, if you look at these formulas, it looks like housing expenses increase with inflation. And then here's these other expenses, which we've taken the forecast as given. In the previous video, we talked about how estimating these in real life can be challenging. And then we've got a total retirement cash flow need for each year with the 25-year investment horizon. And so what return do you have to earn to fund this stream of retirement cash flow needs? If we start out with $600,000, and actually, why don't I copy and paste this so it's right above this so that we have one contiguous cash flow timeline cell range, right? And then to answer this question, we'll use the IRR function again, right? What discount rate gives these future retirement cash flow needs a present value that sums to exactly $600,000? Here's how it would look in Excel. What do I need to earn on my retirement savings to make this work? 6.25%. So these exercises look a lot like some, more second level time value money problems you've seen before. And if you can handle these, you should be in a good spot to approach the fifth assignment. If you have any questions about it, let me know. But thanks as always for tuning in.